Hello, and let's see about the second part of this chapter on optimization. We're going to talk about what is called constraint optimization, by opposition to the previous section, which was really unconstraint optimization. Okay, so what we did last time was we first had a reminder about multivariate calculus. Why? Because the Taylor expansion up to order 2 contains almost everything we need to know to process for the optimization problem. Then we talked about what we could do when we were just optimizing, finding the minimum or maximum values for a function that is twice continuous. So we had some existence results and uniqueness results in simple cases when we were working on compact sets, for instance, or when our function was a coercive function. Right. And then we expressed the conditions. So you remember that we have first order conditions, which are first order conditions we want, which are necessary conditions, which are giving us the candidates for optimum values. So this is mostly if we were looking for minimum or maximum values of some function f on a set A, we were basically looking for the critical points of f, meaning the points that would cancel the gradient of f. Okay, so that's the necessary first order conditions, and then we would have the second order conditions, the sufficient second order conditions, so that we could discriminate between different cases that would correspond to critical points. Basically, that would be the minimum case, the maximum, or the saddle point. Okay, so the second order condition are just sufficient conditions, which will give, which are based on the sign of the quadratic form. If you remember, we make the Hessian matrix of f, so that's the general case. We make the Hessian matrix of f, and we want to know at the critical point, and we want to know the sign of the quadratic form we obtain from this matrix. So we have to study the eigenvalues of this matrix, and I remind you the idea was that if it's all positive, if all the eigenvalues are positive, we are in case of a minimum, so we've got something looking like a convex function, and if all the eigenvalues are negative, we would have a maximum, a concave function. The equivalent of a concave function is several variables, and if ever we've got eigenvalues of several signs, we would be looking at something like a saddle point. Okay, so now we're going to add some constraints to our minimization problem. So let's see what it means.